Okay, good morning, students. Last class we have seen regarding the unsymmetrical triggering. Unsymmetrical triggering for a bistable multivibrator. Okay, it may be a fixed bias or self bias, whatever may be. The triggering circuits will be same. Okay, the triggering method. Okay, whether it may be a bistable or a fixed bias or self bias, okay, whatever may be. We have two types of triggering circuits. One is unsymmetrical triggering, and another one is the symmetrical triggering. Okay, and difference between unsymmetrical and symmetrical triggering is for an unsymmetrical triggering we require two triggering circuits. Okay, on both sides we are going to having a triggering circuits. Okay, these triggering circuits, by using these triggering circuits we are going to triggering the, that means we are going to use to change the state, okay, state of your transistor. Okay, that is the unsymmetrical triggering. We're coming to the symmetrical triggering. But coming to the symmetrical triggering, here we require only a single triggering circuit. Okay, single triggering circuit which can be triggered the both the transistors. Okay, and this is your triggering circuit. Okay, this is your triggering circuit. And this resistance, okay, and this resistance is nothing but sorry, this diode can be offering a resistance to the this part. Okay, simply you can replace this diode with a resistance also. In some cases they are going to replacing this diode with a resistor. Okay, otherwise this diode is offering a forward resistance or reverse bias resistance. Okay, simply this resistance we are using for the this diode we are using for the resistance point of view only, not for the making on and off. We are using it for the in forward. If this diode is in forward bias, it offers some certain amount of forward resistance. Okay, if this diode is in reverse bias, then it offers certain amount of reverse bias resistance. Okay, reverse bias resistance. Simply these, therefore, in some cases they are going to replacing this diode by a resistor. Okay, therefore, whatever may be a simple this resistor. Okay, I am going to say that a simple resistance. Okay, a resistor and capacitor. Okay, this R and C are simply forming a differentiator circuit. Okay, as similar to the unsymmetrical. In unsymmetrical, directly we have taken a resistor. Okay, directly we have taken a resistor and a capacitor, and here we have connected a diode. Okay, and this diode is connected to the base of any on one of the circuit. Okay, therefore these two is forming a differentiator. Similar fashion in symmetrical also, this capacitor and this diode D3. Okay, these two will form a differentiator. Therefore, at this point, you are going to getting a spikes. Okay, you are going to getting a short spikes. Okay, generally we are using the negative triggering. Okay, because negative triggering is more sensitive when compared with the positive. Okay, that means if diode is on, if this transistor is on, in order to make this off, if we apply, if suppose if we assume that this transistor is on, okay, if we apply a negative pulse here, if we apply a negative pulse here of small magnitude, already we have seen in unsymmetrical triggering. Okay, if we, because the voltage at this junction, the voltage at this junction is zero point 0.6, because it is in forward bias. Okay, on stage, therefore the diode will be forward bias and voltage will be zero point 0.6. If you make the voltage less than zero point 0.6, then automatically this diode goes to off state. This transistor goes to off state. Okay, therefore if we apply a small pulse of negative, of it may be a zero point 0.2 or zero point 0.3, minus zero point 0.2 or zero point 0.3 volts, which is going to add with plus zero point 0.6. Therefore here voltage will goes down to resultant voltage will be zero point 0.3. Okay, which is less than the cut down voltage. Therefore this transistor will be moved to the off state. If you see the off transistor, if you see the off transistor, VBE voltage, generally VBE voltage will be a negative here. Okay, therefore we have to apply a positive pulse here. Okay, we have to apply a positive pulse for an off transistor. Okay, in order to make it on, because VBE voltage is negative here. Generally it will be of order of 1 volt or 2 volts. Okay, generally it will be of -1 or -2 volts. Therefore you have to apply a positive pulse which has to overcome this voltage and also the breakdown voltage. Okay, breakdown voltage here, the diode breakdown voltage, that it be a zero point 0.6. Okay, if it is a silicon, here it may be a zero point 0.6. Therefore you have to apply a positive pulse of magnitude around 2.6. Okay, it should be greater than 2.6. Okay, when you apply some around 3 volts positive pulse, then this transistor will move to the on state. Okay, off state transistor will move to the on state when you apply a large positive pulse. Okay, this magnitude should be around 3 volts. Okay, when you apply 3 volts, then it will move to the on state. Okay, I am taking these values as assumptions. Okay, therefore generally, okay, most of the cases it will be a negative voltage, or it may be -1 or -2 volts. Okay, it's a general case. Okay, and for a on transistor, the practically it will be at zero point 0.6. Okay, for a on transistor, VBE voltage will be at zero point 0.6. Okay, in order to make it off, the voltage should be less than zero point 0.6. When the voltage may be it may be a negative voltage, or it may be less than zero point 0.6. Okay, it will goes to the off state. Therefore, this circuit, okay, bistable multivibrator is more sensitive for the negative pulses. Okay, therefore, for an on transistor, generally the triggering pulse will be applied for the base of the on transistor. Triggering pulse is applied to the base of the on transistor, and this pulse is also a negative pulse. Okay, therefore that's why the triggering pulse which I had represented here is a negative pulse. Okay, mostly we will go for a negative triggering only. Okay, for bistable multivibrator or these multivibrators, mostly we will use the negative triggering circuits. Okay, negative triggering circuits. Okay, why we are using negative triggering circuits means your circuit, that means your bistable multivibrator is more sensitive. Okay, that means if we apply a small amount of a negative pulse, there will be a change. Okay, your circuit is going to be change its state by applying a small negative pulse. Okay, we are coming to the positive pulse means you have to apply a large magnitude positive pulse. Okay, therefore it is less sensitive to the positive waveforms. Okay, when you apply a small magnitude positive waveform, your circuit won't respond. Okay, it won't change its states. Therefore, your bistable multivibrator is less sensitive. Okay, it is less sensitive to the positive waveforms, and it is more sensitive for the negative waveforms. Okay, therefore, generally the triggering pulse is a negative waveform. Okay, and coming to the operation of this triggering circuit, suppose this transistor is on. If this transistor is on, then the voltage at this point, okay, voltage at this point will be VBE sat. Okay, VCE set. This is a collector and emitter. Okay, VCE set. Okay, this is the voltage. Okay, generally the maximum voltage will be drop across this resistance. Okay, because high amount of current is flowing. Because it is on means it is nothing but a short circuit. Okay, it is nothing but a transistor is on means collector and emitter are short circuited. High amount of current is flowing due to high amount of current. Okay, more VCC will be drop across this voltage, this resistance. That is the voltage at this point will be nothing but a VCC. That is our apply voltage minus IC. If IC2, okay, if it is a second transistor, therefore IC2 into RC. Okay, this is the voltage at this point, and this drop will be more. This drop will be more because ICRC, okay, IC current is more. Okay, because it is short circuit. Therefore, here we are going to having a VCE set. It will be around a 0.2. Okay, if we go for a practical case, it may be a 0.2 or 0.3 volts. Ideally, you can make it as a 0. Therefore, this voltage, okay, this voltage is very minimum. Ideally, we can say that this voltage is 0. Therefore, this diode, okay, this diode will be in reverse bias. Okay, anode voltage is less than, which makes this diode off. Therefore, you can take any transistor. Okay, if this transistor is on, if this transistor is in on state, this diode will be in reverse bias. Okay, yeah, that means the which diode for which the a collector connected, okay, diode will be on transistor collector connected diode will be in reverse bias. Okay, I have taken this as on, therefore D2 will be in reverse bias. Okay, if you take Q1 as on means here the voltage will be minimum and make this diode in reverse bias. Okay, you can take any side. Therefore, when this diode is in reverse bias, if we apply a triggering pulse, and you have to consider the voltage at this point also. Okay, if you see the voltage at this point, this transistor is an off state. Therefore, it is a open circuited. Okay, it is a open circuited. If it is opened, there is no current. Okay, ideal case you can say that in practical there may be a leakage current. Okay, if ideal case there won't be any current flowing in this resistance. Therefore, drop across this one will be 0 volts. Okay, because there is no current. Therefore, this VCC will be present at this point. Okay, VCC will be present at this point. Therefore, this anode is at higher potential. Okay, you have to remember that for our entire circuit, the maximum voltage is VCC. Okay, you have a different voltages. Okay, here we have a VCC, here we may have VBB, and here we may have VCE voltage, VBE voltage. Okay, if you take all the voltages among in any electronic circuit, not only this circuit, in any electronic circuits, the maximum voltage in our circuit will be a VCC voltage. Okay, and remaining voltages, okay, remaining voltages in our circuit will be less than the VCC voltage only. Therefore, here at this node we are having a maximum voltage. Therefore, this voltage makes this diode in forward bias. Okay, because anode is connected at the higher potential. Okay, anode is connected to the higher potential, makes your D1 has the on. Now, if we apply a triggering pulse, negative triggering pulse, it will be travel. This because it is off. Okay, it will traverse through the D1. It will traverse through the D1 unto the R1 resistance, and it will be applied to the base of your second transistor. That means this negative pulse will going to travel from the diode D1 unto the collector and through this R1 resistance unto the base of your on transistor. Therefore, we are going to applying a negative pulse to the base of the on transistor, which makes this transistor off. Okay, therefore this negative pulse, we had applied a negative pulse to the base. Therefore, it makes this transistor off. When this transistor is off, okay, when this transistor is off, it is a open circuit. It is a open circuit, and voltage at this point, okay, and it makes the voltage at this point to the VCC. Okay, because it is an open circuit, there is no current flowing in this branch. Okay, therefore the voltage at this point will be a VCC and makes this diode on. Okay, and the voltage, because this is on, therefore it will be a short circuit. Okay, therefore the drop will be more here, and it makes the voltage here at this point will be minimum and makes the D1 in reverse bias. Okay, and if we apply the second time triggering pulse, okay, after some time if we apply again triggering pulse, now this diode is on. Therefore, the negative pulse will be traveled through this waveform or through this D2 and through this resistance and to the base of the on transistor, which makes the Q1 off, and again Q2 will be becomes on. Okay, therefore a single pulse is going to be transferring the is going to applying for the both the transistors. Okay, a single pulse is going to applying for the, if you want to apply the gate pulse for, because that means at if Q1 is on, we can by using this pulse we can apply to the base of the Q1. If Q2 is on, by using the same triggering pulse we are going to applying the triggering pulse to the base of the Q2. A single triggering pulse circuit is used to provide the triggering pulses for the both the transistors. Therefore, it is a symmetrical triggering. It comes under the symmetrical triggering. Okay. Last class we have seen the unsymmetrical triggering. There we have connected the two different circuits. Okay, two different circuits. That means the diode. Okay, the major difference that is there, the diode is connected outside your circuit. Okay, this is your circuit. Okay, you may have the resistance and you may have the capacitor. Okay, therefore this voltage, okay, the voltage of this one will be on only this diode, and it won't affect at this point. Okay, therefore here we may have the another diode. Okay, here we may have the another diode which is going to be connected to your through a resistor and a capacitor. Okay, therefore voltage at this point won't affect this one, and voltage at this node will not affect this one. Okay, therefore both are separate circuits. Okay, we require two different circuits for unsymmetrical. Okay, for unsymmetrical we require two different circuits. For a symmetrical we require a single circuit. Okay, this is regarding your triggering circuits. Okay, therefore a complete diagram. Okay, that means a bistable multivariate means here we may have one more diode which is your catching diodes. Okay, it may be in this direction. Okay, this is your catching diodes. Okay, therefore this is your catching, and here we have to apply a voltage, some V volts. Okay, which is less than VCC. Okay, and this is a speed up capacitors. These capacitors are the speed up capacitors. Okay, and this is your complete bistable multivibrator. Okay, this is your complete a bistable multivibrator. That means for this circuit, we have apply a triggering pulse, we have apply a collector catching diodes, we have apply a speed up capacitors, and we have to make the all the parameters. Okay, yeah, therefore this circuit you directly you can connect in lab. And by applying a triggering pulse, okay, you can apply by using function generator. Here you can connect a function generator. Okay, I think so. Next semester you may have the lab. Okay, pulse and digital circuits lab you have. In lab you have to construct this one. Okay, in lab you have to construct. Okay, here we are going to connecting a this one. Okay, function generator. In function generator we are going to using the a square wave has the input. Okay, and we are, if we are applying a triggering pulses here, it is going to, and if you connect a CRO here, if you connect a CRO here, here you may get the this type of waveforms. Okay, on and off. Okay, on and off waveforms you are going to get. Okay, this is your bistable multivibrator. Okay, bistable multivibrator, and this is nothing but a collector couple. Okay, already at the time of starting, I have said the two types of multivibrators. Okay, two types of multivibrators. One is collector couple, another is emitter couple. Okay, emitter couple is nothing but we are going to call as a Schmitt trigger. Emitter couple is nothing but we are going to call as a Schmitt trigger. Okay, and this collector couple are nothing but which you have these in these two. Okay, collector couple bistable multivibrator are nothing but a self biased and fixed biased. Okay, for self biased and fixed biased, we have get a different drawbacks. Okay, when you connect a load, okay, when you connect a load at this point, okay, the response of the system is very slow. Okay, therefore, you know, to overcome these two drawbacks, we had making some changes. Okay, we had making some changes to the basic circuit, and then we have seen the triggering circuits, and then we have seen the triggering. That means, in order to change its state, definitely you have to apply triggering first, because it is going to having a two stable states. That means, if you want to apply triggering first, it will be maintained only at one. Okay, it will maintain only at one stage. Okay, when you apply triggering first, then only it will goes to the zero. Okay, if you want to apply one, it will be present at the same stage only. Okay, and if we when you apply triggering first, it goes to zero, and it will maintain at this stage only. It won't change its state, because the bistable multivibrator having a two stable states. Okay, how we can say that two stable states means, here both are coupled with a DC coupler. Okay, the input of the transistor, okay, the input of the Q1 and Q2 are coupled with the DC coupler. That this resistor we are going to call as a DC coupler. As we had explained before, this resistance we are going to call as a DC coupler. If in place of resistance, if we place a capacitor, then we are going to call it as an AC coupler. Okay, if we have a reactance, simply capacitor is nothing but a reactance. Okay, if you couple the transistor by using a reactance, then we are going to having a quasi-stable state. For a monostable, you may have the one resistor and one capacitor. Therefore, it is going to having one stable state and another quasi-stable state. For stable, both are capacitors only. Here you are going to place the capacitors only, which makes both are quasi-stable state. Okay, I think so. You have remembered the what do you mean by quasi-stable state and what do you mean by stable states. Okay. Therefore, this is regarding your collector coupled bistable multivibrators. Next, we will move on to the emitter coupled. Emitter coupled bistable multivibrator is nothing but your Schmitt trigger. Okay, this is your last concept. Okay, this is the last concept in your third chapter, and then we have to solve some problems. Okay, we have some problems on Schmitt trigger, and we have a small derivation. We have a small derivation for this Schmitt trigger. After this derivation, we have to solve the problems of Schmitt trigger, and similarly, we have to solve the self-biased problems also. Okay, we have seen only fixed biased problems. We have to solve the self-biased problems. That means, after this concept, mostly theory part. Okay, theory part of your third chapter is completed. Only we have a problems. Okay, only we may have the problems. Now we will start our class. Next topic is this Schmitt trigger. Okay, we are going to discussing regarding this Schmitt trigger. Okay, this is nothing but a emitter coupled bistable multivibrator. This is nothing but a emitter coupled bistable multivibrator. Where for this one also, if we observe, it is a DC couple. Okay, because the output or input of the second transistor is connected from the collector through a resistor. This is nothing but speed of capacitor. Therefore, this is our basic circuit. It is connected with a resistor, which is a DC couple. Therefore, it is going to having a stable state only. And the second modification here we have seen that generally from the output of your second transistor, it is connected to the input of your first transistor. That feedback has been not present in this Schmitt trigger. That is the change. Okay, that is the change you are going to observe. The change is nothing but here we are going to having only one regenerative feedback. Okay, in previous circuit, you are going to observe the two. You are going to see the two regenerative feedbacks. Okay, you have seen the two regenerative feedbacks. That is your previous circuit, bistable multivibrator, emitter coupled bistable multivibrator, collector coupled bistable multivibrator, where we are going to see the two. Okay, here we are going to having only one. Okay, this is the difference. Okay, this is the base of the second transistor connected through the resistor from the first transistor, collector through the first transistor. Similarly, in this way, they were coming to this Schmitt trigger. We have only one regenerative feedback. We have only one regenerative. There we have a two regenerative feedbacks. Okay, how many regenerative feedbacks? It may not affect our circuit. The circuit, in order to get, in order to operate, has a multi-vibrator. It will depend upon the loop gain. Okay, already we have seen in introduction classes the loop gain. Okay, the loop gain of your multi-vibrator should be very less. Okay, depending upon the whether it is having the greater than one or less than one, we are going to operating it as a bistable multivibrator or has an amplifier. Okay, simply a regenerative feedback amplifier. Okay, therefore, in order to operate it in as a bistable multivibrator, your loop gain should be a less than one. Okay, the loop gain should be a less than one. Okay, if it is less than one, then we are going to operating it as an bistable multivibrator, or simply a multivibrator. It is going to operating as a multivibrator. If the loop gain is greater than one, then it is going to operating simply amplifier. Okay, it is going to operating as a amplifier. Therefore, if we have a two feedbacks, that means two regenerative feedback. This is nothing but a regenerative feedback. The output is connected to the input. Okay. Therefore, if we have a two, the overall loop gain we have to check. That means combination of the two loop gains. Okay. That means output by input of the first one, second one also output by input. Okay. If you combine these two, the loop gain should be a less than one in order to operate as a bistable multivibrator. If we have a single regenerative feedback, then the single we will take it. Okay, the gain should be less than one, then it is going to act as a bistable multivibrator. Okay, depending upon this R value, depending on the R values, the loop gain is going to be changed, and correspondingly, you may have the you may have this one. Okay, you may have the loop gain also, depending upon, we will see the designing aspects. Okay, by solving the problem, we are going to designing this RC1, R1, RS. Okay, and one more difference here you are going to observe it. There also both transistors emitter. Okay, both transistor emitter are grounded, but here the both transistor emitter are connected and grounded through a resistance. Grounded through a resistance RE. Okay, this is another difference. Okay, first difference is we had emitted the we are not given the second regenerative feedback. Okay, we are not given the second regenerative feedback, and second change is the both emitters are you can observe the previous diagram. Okay, you can see it in previous diagram. Here both emitters, okay, both emitters are looped and grounded. Okay, and grounded, you can take it as separately or you can combine it both, and you can place the separate ground here. Okay, you can take the two grounds separately. Otherwise, you can loop it and you can show it as a single ground. Okay, nothing is wrong. Okay, it is grounded, simply grounded. Now, for a symmetrical, here we are placing a resistor and then grounding. Okay, we are going to placing the resistor and grounding. Okay, this is the second difference. These both are the emitters. Okay, emitters are combined and then we are connecting a resistor and then grounded. Okay, and for the base of the first transistor, we are going to providing an input signal. Okay, we are going to providing an input signal. It may not be a DC, it is a AC. Okay, a sinusoidal signal. A sinusoidal signal we are going to applying at the input. Okay, input of your first transistor, and this is the your output. Okay, we are going to collecting output from the second transistor. Okay, output is taken from the second transistor for the base. Okay, you can treat it as a triggering pulse. Okay, you can take it as a triggering pulse. Okay, whatever may be, we have to apply an input waveform. Okay, we have to apply an input waveform to the base of the first transistor. Okay, now we will see the what happens. Okay, what happens we will see. Generally, if we are having a AC waveform, okay, AC waveform, it may start from zero. Okay, it may start from 0. Therefore, initially the voltage at this point, okay, I am saying at t equals 0 seconds. Okay, the voltage will be a 0. Okay, the voltage is 0 means there is no current flowing to the base of the transistor. Therefore, this Q1 is in off state. Okay, initially the Q1 will be in off state. That means this is an open circuit. Okay, if it is in off state, what happens? The voltage at this point, okay, the voltage at this point, this is an off transistor. Therefore, there won't be any current in this path. Okay, there won't be any current. That means this IC1 will be minimum, or you can take it as 0. Therefore, the voltage at this point will be VCC. Okay, voltage at this point will be VCC. Therefore, here there is a sufficient voltage which drives the current to the base of your second transistor. To the base of your second transistor, and make this transistor on, Therefore, here this transistor is a short circuited. Okay, because we are driving the base current. When a base current flows through a transistor, the transistor moves to the on state. Okay, therefore this transistor is on and this transistor is off at the time of starting. Okay, at the time of starting of your input voltage. Okay, now what happens? Okay, when this transistor is on, there is a current flowing in this branch. Because this is a short circuit, there is a current flowing in this branch, and due to that current there will be a drop across this resistance, and therefore the voltage at this point, that means nothing but a output voltage. Output voltage is nothing but a VCC minus IC2. Okay, IC2 into RC. Okay, this is our output voltage. Okay, this drop will be very more, ICRC. Okay, ICRC drop will be very more, and therefore this voltage will be very less. Okay, generally it will be a 0.2 or 0.3. Okay, you go for practical. Therefore, you can say it is an ideal case. You can take it as a 0. Okay, therefore our output is maintained at 0 level, or it may be a 0.2 or 0.3 volts. Okay, and now on the same current. Okay, the same current is flowing through from the collector, because this is an on transistor. Same current it will flow through the IE. IE is nothing but a IB plus IC. Okay, IE is nothing but a, here in this path IE current is flowing. IE is nothing but a, in this direction IB current is getting. Okay, from here IB current is getting, and here IC current is getting. If we assume that IC is very small, IB is very small, base current will be generally in microamperes. Okay, this will be in milliamperes. This is very small current, base current. Therefore, we can neglect the base current. Therefore, it is nothing but IE equal to IC. Simply IC2. Okay, simply IC2. IE equal to IC2. This current will flowing through this emitter resistance. Same current. This is not connected. Okay, this is a overlap. Okay, therefore the same current is flowing through the emitter. Same current is flowing through the emitter. Therefore, here it is creating some voltage drop. That is nothing but a IE-RE drop. Okay, this IE-RE drop, which if we observe for a off transistor, from off transistor, if we observe this voltage makes this base to emitter. Because if it is an NPN transistor, this is a N. Your collector is N, base is P, and this emitter is N. And current is entering in this direction. Therefore, the voltage, this will be in positive and this will be negative. The positive terminal is connected to the negative of your transistor. Okay. Therefore, this make your base emitter junction to be off state. Okay. Therefore, this voltage, okay, whatever the voltage present in our emitter resistance, make this off trans, that means your Q1. Okay, Q1 in reverse bias. Okay. Therefore, your input voltage, okay, when the input voltage reaches greater than this drop across RE. Suppose the drop across RE, if we have it 3 volts, okay, let us assume 3 volts. Then if the input voltage is greater than 3, and there will be some forward voltage drop also here, because it is a diode. In order to make this diode, you have to apply 0.6 volts. Okay? Therefore, when the input voltage reaches greater than 3.6, greater than 3.6. Why I have taken 3.6? If I assume the voltage across RE is 3 volts, okay, if this is 3 volts, and here there will be a cut down voltage, that will be a 0.6. Therefore, our input voltage is greater than that voltage, sum of 3 volts. That we can take it as an VE voltage plus VBE. Okay, VBE of your first transistor. Okay, VBE of first transistor. Okay, VE is nothing but a IC2 into RE. Okay, because the second resistor is on, therefore second current IC2 current is flowing IC2 into RE. Therefore you can take it as an VE. Okay, this voltage drop is nothing but a VE. VE plus VB. Okay, when your input voltage is greater than this voltage. Okay, when input voltage is greater than this voltage, then it make this transistor on. Okay, then only this transistor Q1 becomes on. Okay, whenever your input voltage is less than this voltage. Okay, less than VE voltage plus VBE. Okay, which is less than that voltage, then your transistor will be in off state only. Okay, therefore this voltage we are going to call as an upper threshold voltage, upper UTV. Okay, upper threshold voltage, or simply you can take as a this point. Okay, this point on this voltage is nothing but upper threshold point, UTP. Okay, they may call it as a UTP also. The upper threshold point, upper threshold voltage at upper threshold point. Okay, voltage at upper threshold point is nothing but upper threshold voltage. Okay, therefore whenever input voltage is greater than upper threshold point or upper threshold voltage, then only this transistor becomes on. Okay, once the Q1 is on, when the Q1 is on, this in this direction current is flowing, therefore there will be a more drop at this point, and voltage at this point will be minimum. Therefore it won't drive the sufficient current, sufficient base current for Q2, and makes Q2 has off. Okay, up to now what we have discussed, this Q1 is on. Due to Q1 you are getting a current here, that current, due to that current we are getting a VE voltage drop across this resistance, and here you may have a VBE voltage, VBE1. Okay, simply this is the first transistor, VBE1 voltage. When the sum of these two voltages, okay, your input voltage is greater than sum of these two voltages, then only this transistor will be on. Okay, when this transistor is on, this is a short circuited. Okay, therefore there will be a more current flowing in this branch. Okay, there will be current flowing in this branch. Due to that current, there will be a more drop across this resistance, and voltage at this point. Okay, the voltage at this point will be very less. Okay, therefore this voltage may not sufficient to drive the current. Okay, previously our voltage is at 0. Okay, may not be sufficient to drive this transistor. Therefore this transistor moves to the cutoff zone. When it moves to the cutoff, it is a open circuited. When it is a open circuited, the current will be very less, or you can take it as 0 current. There won't be any drop here. Therefore at this point voltage is nothing but a VCC. Okay, therefore this is nothing but a practical if you saying that VCC minus IC2. Okay, IC2 RC. Okay, this is the voltage at this point. Okay, practical, ideally we can take it as a 0, and at this point you may take it as a VCC. Okay, therefore our voltage will be VCC. Okay, because this transistor is off. Okay, therefore now we are flowing the current in this direction. Okay, the current is moving in this direction, that is nothing but IC1. Okay, this current IC1, this IC1 current will flows through this transistor. Okay, so this emitter resistance. Okay, therefore due to this IC1 current, there will be a new drop across this resistance. We may call it as a V dash. Okay, V dash or VE dash. Okay, simply VE dash is nothing but due to the first transistor collector current. VE is nothing but due to the second transistor collector current. Okay, this is nothing but IC1 into RE. IC1 into RE is nothing but a V dash E. Okay, this is our voltage. Okay, and now this voltage make this transistor Q2 in reverse bias. Q2 in reverse bias, because this is also same transistor. We have to take two identical transistors. This is also an NPN transistor. Therefore, this is a N. This is N, which is kind of flowing in this direction. Therefore, you can take it this as positive. Positive is connected to the N terminal. Therefore, here we are going to getting a negative voltage. This negative voltage, okay, and this is a off transistor. Therefore, here we may have a VBE2. Okay, we can take it as a VBE2. Therefore, here we are going to having a new voltage VBE2. Okay, VBE2 plus V dash E. Okay, when this is the voltage, make this transistor off, and this voltage we are going to call it as a lower threshold voltage. Lower threshold voltage. That means in here we have seen the two voltages, upper threshold voltage and lower threshold voltage. Okay, that means your input voltage is moving in the two directions. Okay, that means when your voltage is greater, that at this point you may have an upper threshold voltage. Okay, and at this point you may have the lower threshold voltage. Okay, that means when it is upper, when your input voltage crosses the upper threshold voltage, make the Q1 on. Okay, when the input voltage crosses the lower threshold voltage, makes the Q2 on. Okay, when your voltage is greater than the this voltage, lower threshold voltage, your Q2 becomes on. Okay, and again you may have this voltage falls to the zero. Again this voltage falls to the zero. Therefore we have a two voltages here. Okay, upper threshold voltage and lower threshold voltage. At the upper threshold voltage, Q1 becomes on. Okay, at the lower threshold voltage, Q2 becomes on. Okay, therefore your circuit will be oscillate. You are correcting the output at this point only. Okay, therefore this is the output point. Therefore your output may be changes from where this voltage VCC minus ICRC into VCC level, and again it will falls to the same level. Okay, therefore your output may you are going to get a pulses. Okay, you are going to get a pulses like this. Okay, this is regarding our symmetrical. Okay, that means simple theory. Okay, we have to derive the expressions for upper threshold and lower threshold voltages. Okay, we will see it in next class. Simple theory regarding this theory is nothing but due to this RE resistance. Due to this RE resistance, your transistor will be going to the voltage across this RE makes your transistor on and off. Okay, make your transistor on and off. This is the key point. Okay, key element in our circuit. Okay, due to the voltage present at this resistor, okay, RE resistance, make your transistor on and off. Okay, therefore this is regarding our Schmitt trigger. Regarding our Schmitt trigger. Okay, therefore you have to take the input voltage as a sinusoidal which is moving from the zero. Okay, where when it is zero, this transistor is off state and this will be becomes on state, and when this voltage crosses the threshold point, upper threshold point, then this transistor will be goes to the on state and this transistor will be goes to the off state, and again it moves to the lower threshold point. Okay, when it moves to the lower threshold point, makes this transistor on and make this transistor off once again, and again if it moves to the upper threshold point, again it will becomes on. Okay, like that. In this case there is no need any triggering pulse. There is no need any triggering pulse. We have to set this RE resistance. We have to set the RE resistance. Depending on RE, we can adjust the VE voltage. We can adjust the VE voltage, and depending on that, you may adjust the upper threshold voltage or lower threshold voltage, so that it may take you more time. If this VE value is very large, that means if RE value is very large, then IE into RE. Okay, that is nothing but our voltage is very large. Ganesh sir, అవునా? అవును. అది పిఎన్ఎస్ దగ్గర ఉంది అడ్మిన్ అది. ఇవాళ ఇంకా అయితే. అడ్మిన్ నేను అడ్మిన్ మర్చిపోయాను. స్టాఫ్ అందరికి ఇచ్చింది నేను చేస్తా ఉండు. నేను క్లాసు అయిపోయింది. క్లాస్ ఎండ్ చేస్తున్నాను, ఇస్తాను. చెప్పాను, పిల్లలకి చెప్పాను నేను. చెప్పాను. నా క్లాస్లో ఉన్నాను, ఎండ్ చేసి పిల్లల్ని జాయిన్ చేపిస్తాను దాంట్లో. చదువుతుందాం. ఓకే అమ్మా. ఓకే ఫైన్.